This is section 7.7. Today we're going to be working with periodic functions. So a function is said to be periodic of period t, where t isn't equal to 0, if f of t plus this capital T, our period, is just equal to f of t. And that's true for all t in the dominion of f. Let's make it confusing with our little t's and our big t's. So for a periodic function, you can picture something like a sine wave, where it just keeps repeating itself. You can kind of chop it up into little windows where it keeps repeating itself. So a windowed version of a periodic function looks like what you take when you just look at the period. So in this way, we're going to take the function and we're going to multiply it by our window function from the previous video. So in this way, I would take, remember what the window function looks like. It's all 0 until it's equal to 1 at some point, and then it stops being equal to 1. So it's just 1 over a small bit, and then everything else is 0. Well, if we multiply that 1 by any function we want, we can have the window display anything. So in this case, it may display something like our sine period. And we're only going to show one window of it. So the window function, if you define it to go from 0 to capital T, so that would represent one period, then you don't notice any periodic nature. You just notice the period, and where it starts to repeat is cut off. So explained algebraically, you take the unit step function at t and you subtract the unit step function at t minus this capital T period. So in this way, you are viewing your function f of t one period between 0 and capital T, and then you're stopping. It's equal to 0 everywhere else. So let's let capital F of s equal the Laplacian of a function f. And we'll suppose that f has period t, and it's piecewise continuous, exponential order, all that stuff we need to have Laplacians exist. Then this Laplacian of f is, of course, by the definition, equal to the integral from 0 to infinity of e to the negative st times the function f of t. Suppose that f of t is difficult to calculate. We have other methods. We're going to use this window function. So if we take our window function and we look at its Laplace, so we have a function f, let's get them all straight here. F is something periodic, like a sine wave. F of t is that sine wave cut off after a single period. Capital F is the Laplacian of f, and capital F sub t is equal to the Laplacian of ft. Well, the Laplacian of ft, we just plug in ft into the definition of the Laplacian, but we can simplify this somewhat because this integral doesn't need to go all the way to infinity, because since we're only looking at a single period, after we reach our t is equal to capital T, along the x-axis there, everything is 0 after that point. It's all 0 because of the way the window function works. So we can stop integrating at that point. So we only need to integrate from 0 to capital T. Now, the usefulness of this from the book, we have that the Laplacian of f sub t is equal to the Laplacian of f times 1 minus e to the negative st. So in trying to calculate things of this nature, we're going to make use of this identity. So now we're going to do an example. Solve question 2 from the textbook. Determine the Laplacian of f, where f is the function e to the t from 0 to 1, periodic with period 1. So let's look at what this looks like. E to the t is an exponential function, kind of goes up and up and up, but we're going to stop at t equals 1. And we're saying that f is actually periodic with period 1. So it just keeps repeating this over and over. And this is what our function looks like. So by our formula, the Laplacian of this function is equal to the Laplacian of the windowed function divided by 1 minus e to the negative st. Remember, the windowed function would just take one of these periods. So the window function is just going to go from 0 to 1. And that's the first thing we're going to calculate is what is capital F sub t, the Laplace transform of the windowed function. Well, the windowed function is just, let's remember what our rectangular window function is. It's 0, and then it's equal to 1 until we reach our stopping point. Here it's from 0 to 1. And then it just goes back to being 0 forever. So that's the window function. If we multiply that window function by e to the t, multiplying 0 by e to the t just stays 0. So everything that was 0 stays as 0. But this 1 here is actually going to become e to the t. And this is exactly the function that we're trying to solve for. So this is a proper representation of little f. It is e to the t times the rectangular window function from 0 to 1. Well, we know algebraically what that rectangular window function is. It is u of t, the unit step function of t, minus u of t minus 1. We'll explain that. The unit step function of t is 0 all the way up till you get to 0, and then it's 1 for everything that's positive. If I were to take the unit step function of t and subtract u of t minus 1, so take this and subtract this function, that's going to equal this function, where this 1 minus this 1 just gives us 0. This 0 minus this 0 just gives us 0. The only place that isn't 0 is where I have 1 minus 0. So that gives me 1. So that's how you can create a rectangular step function, rectangular window function, by subtracting unit step functions. Now, of course, this isn't as simple as just 1. We have e to the t. So we're going to take our unit step functions and multiply them by e to the t. And we're going to try to calculate the Laplace transforms of these. Well, from our table, and not just from our table, also from our rules in, I believe, 7.6 regarding these unit step functions, we know how to calculate these Laplace transforms. The Laplace transform of e to the t times the unit step of t is just 1 over s minus 1. And the Laplace transform of e to the t times unit step of t minus 1 is e to the negative s times the Laplace of e to the t plus 1. Now, we've dealt with the Laplace of e to the t before, but never e to the t plus 1. But thankfully, we can simplify this easy enough because e to the t plus 1 is equal to e to the 1 times e to the t. So I can just factor out an e to the 1, and it comes outside here. And I know that the Laplacian of e to the t is 1 over s minus 1. So I have this value for capital F sub t, or the Laplacian of little f sub t. Joining them together, we already have a common denominator. But we have an identity. We know that capital F is going to be equal to this value, capital F sub t, divided by 1 minus e to the negative st. So I have to take what I just solved for. I know this is capital F sub t, and I have to divide it by 1 minus e to the negative st. And that's how I get my final solution. Note that this t right here was stated in the problem as being equal to 1. So that's why it just kind of cancels out here, because s times 1 is s. And we'll just scroll back up to show right here periodic with period 1. That's your capital T value. So this is our final solution. What capital F represents is the Laplacian of this function that just keeps repeating e to the t from 0 to 1. Okay, now we're going to solve question 4 from the textbook. Determine the Laplacian of f, where f is this piecewise function. It's equal to t from 0 to 1, and it's equal to 1 minus t when t is between 1 and 2. And we're saying that has period 2. So let's draw this graph just for some understanding here. From 0 to 1, it's t. But then from 1 to 2, it's 1 minus t. So it looks like this. And then it will keep repeating as such. So we're going to use our formula. Capital F is equal to capital F sub t divided by 1 minus e to the negative st. In this case, we're going to be plugging in 2 for that capital T instead of 1 because the period is 2. And we're going to start as before with calculating capital F sub t first. So capital F sub t, remember, is the Laplacian of the function that just shows the period once and has everything else equal to 0. So the Laplace transform of the windowed function, remember this is just the window from 0 to 1 times t. We're going to have to break this up because it's piecewise. So from 0 to 1, it's t, but from 1 to 2, it's 1 minus t. So we have to take our window from 0 to 1 and multiply it by t, and then add that to our window from 1 to 2, multiplied by 1 minus t. Now, we know what these window functions actually are in terms of step functions. This is equal to u of t minus u of t minus 1. And this is equal to u of t minus 1 minus u of t minus 2. Now we're going to use the linearity of our Laplace transform to carry it through. So we take the Laplace of this and subtract the Laplace of this, and so on. So we now have 4 Laplace transforms that we are going to try to solve. And these will all be solved using our rules from the previous section. So the Laplacian of t times u of t is 1 over s squared. The Laplace of t times u of t minus 1, well, remember that's when you're looking at things of the form g of t times u of t minus a. And that rule states that it's going to be e to the negative s times the Laplacian of t plus 1. Here we have the Laplacian of 1 minus t times u of t minus 1. That's going to give us the Laplacian of u of t minus 1. So we're going to look at how this has actually been broken up because, yeah, there's a couple steps in here, so we'll explain. So the Laplacian of 1 minus t times u of t minus 1. What we're doing is expanding this to become the Laplacian of 1 times u of t minus 1 minus the Laplacian of t u of t minus 1. So that's how we've broken this up into 2 pieces. So the Laplacian of u of t minus 1 is the first bit, and the second bit is the Laplacian of t times u of t minus 1, of course, with this negative sign carried through. And we do the same thing with our last piece here. That 1 minus t in there is going to break this up into a sum. So we get the Laplacian of u of t minus 2 plus the Laplacian of t times u of t minus 2. And now we can further apply our rules from the previous section. The Laplacian of t plus 1 carries down here. As 1 over s squared plus 1 over s. And we bring through our negative e to the negative s multiplied. The Laplacian of u of t minus 1, that's e to the negative s over s. The Laplacian of t times u of t minus 1 is e to the negative s times the Laplacian of t plus 1. We've actually already solved that in a previous step earlier. The Laplacian of u of t minus 2 is right here. And the Laplacian of t u of t minus 2 is right here. And these all follow by those 2 or 3 rules that we learned in the previous section, depending on the form, whether it's f of t minus a times u of t minus a, or if it's g of t times u of t minus a. We have rules for calculating those Laplacians. From there, we're just going to finish by calculating what the Laplacians are of t plus 1. But they're very simple. That's just 1 over s squared plus 1 over s. And then we group our like terms. So we finish with 1 minus 2e to the negative s minus se to the negative s plus 2 plus e to the 2, oh my, plus e to the negative 2s over s squared. And now that's f sub t. So if we want to get f, we have to take that value and divide it by 1 minus e to the negative 2s. So this is our solution.